Okay, so here we are again. We are still investigating properties of the cross product, also known as the vector product. What we have seen now is a quick computational way to compute the cross product, and the purpose of this video is to see the geometry of the cross product and what it actually means. So first of all, when we have a vector like this vector right here, u, and we do the cross product with another vector v, we use the right-hand rule, and the result is a vector which is perpendicular or orthogonal to both of these vectors, pointed in the direction using your right hand, which would be pointing in the direction of your thumb. Now this is the magnitude right here. It's the magnitude of u, magnitude of v times the sine of theta. And then n is a unit vector pointed in the direction using the right-hand rule. So the magnitude of n is automatically equal to 1 because it's a unit vector. So what that means is that the rest of that blue highlighted part is the magnitude of the cross product. The magnitude of u cross v is equal to magnitude of u, magnitude v, sine of theta. Okay, so that's kind of cool. If we happen to know what theta was, because we had previously used perhaps a dot product to find it, then we could find the magnitude of the cross product. Okay, but there's a little more to the geometry that's interesting. Okay, so let's consider this parallelogram that I've drawn here. It has a base and a height. And we've seen before that if we wanted to find the area of a parallelogram, the area is equal to the length of the base times the altitude or the height, and that's the area. Okay, so as long as we remember that, here's the height, and here's the base. We are using this to find the area of a parallelogram. So then you ask, well, how does that relate to the cross product? And I'm going to show you. Okay, so here are two vectors, u and v, and the angle theta between them. And if I were to think about completing this to make it into a parallelogram, it might look something like this. Like that. And so the sides are the vectors u and v. Further, if I were to drop a perpendicular down like this, make that a right angle, and call this h, then I can see that the area of this parallelogram is equal to the length of u, which is the magnitude of u, times the height. Right? Okay, well, what's the height? In order to get an expression for height, I'm going to use some trigonometry. The sine of theta is equal to the opposite, which is h, over the hypotenuse, which is the magnitude of v, which means that the height is equal to the magnitude of v times the sine of theta. If we substitute that in for this h right there, what do we got? Well, then we have the area of that parallelogram is equal to the magnitude of u times the magnitude of v times the sine of theta, and that is equal to the magnitude of u cross v. So we can use that in a couple different ways. One way is we could say, well, if we have a vector u and we have a vector v and we make a parallelogram out of it, the area of that parallelogram is equal to the magnitude of the cross product of u and v. All right, so let's do it. You may recall these vectors from the last video. That is, u was 3, negative 2, 1, v is 2, 4, 3. And we computed the cross product. So we already found that u cross v was equal to the vector negative 10, negative 7, and 16. And that's those are two vectors in space pointing in different directions, and but you can think of them as starting at the origin. All right, well, what's the area of the parallelogram with u and v as edges? or sides? Well, it's just the magnitude of u cross v, which is the square root of -10 squared plus -7 squared plus 16 squared. So that's the square root of 100 plus 49 plus 256, which is the square root of 405. And I'm sure that's what you were thinking it probably was. Okay, so what does that mean? That means we have two vectors which are possibly pointing in different directions in weird ways. One's like this and one's like that or something. But if we were to take a copy of u and a copy of v, then what we've found is the area of the parallelogram with edges formed by u and v is the square root of 405. Okay, so if you wanted to now find the area of a triangle with sides formed by u and v, you can just cut the parallelogram in half, right? You get half of the area, just right down there. The area of the triangle is equal to the magnitude of u cross v divided by 2. All right, thank you very much. Bye.